Here we're going to be talking about solving systems of equations. In this case, we'll be using elimination quite a bit. And we'll talk about some special circumstances that can happen when solving a system. First, let's do a little bit of a review. So if you're comfortable solving systems of equations, you could skip ahead to example number 2. So here, in this first system, this first example, remember our first step is to create opposites. And I do not see the opposite of negative 6x is positive 6x. Opposite of 9y is negative 9y. So there's nothing I can multiply that top equation by to either get opposite x's or an opposite y. So I need to think about what number does 4 and 6 multiply into, or what number does 8 and 9 multiply into, and then create opposites with that least common multiple. I know the least common multiple of 4 and 6 is going to be smaller. It means the multiplication will be easier because the least common multiple of 4 and 6, let's see, here's my multiples of 4. I'm not sure exactly where to stop. The least common multiple of, or the multiples of 6 is 6, 12, 18, 24. So a lot of people just multiply 4 and 6 together to say, hey, the least common multiple is 24. Well, that's a common multiple, and that's okay. We could multiply this by 6 and this by negative 4 to create opposite 24s. We could instead create opposite 12s, and that's what I'll do here. So I'm going to multiply the top equation by 3. That's going to give me a negative 12x. And I'm going to multiply the bottom equation by negative 2. That's going to give me a positive 12x. So that's how we take our time. We figure out what the least common multiple is, what number, or in other words, what number 4 and 6 multiply into, and then we do multiply to create those. Now we need to multiply that to everything in the equation. We need to distribute that through. I'm going to get rid of this right here, free up some space. So as I continue distributing on the top equation, I get negative 24y equals negative 60. And on the bottom, distributing the negative 2 through, I get negative 18y and positive 60. So now that we've created opposites, now that there are opposites in this new system, we can add. So the negative 12x plus positive 12x is 0. Here we get negative 42y equals 0. Divide by negative 42. So y equals 0. Now we plug that back into one of the original equations to solve for x. I'll use the bottom one, but it doesn't matter. Both should give you the same solution that we're about to get. Now 9 times 0 is just 0, which really from here we don't even need to write it. Typically you'll not get 0 and then you have to undo that thing. But subtracting 0 doesn't change either side either. So really we have negative 6x equals negative 30. So we just divide by negative 6. We get x equals 5. So what does this mean? It means that the one solution that these two equations have in common is exactly the same as 5, 0. On a graph, so that would show up in both tables. If I made a table of these solutions for the top equation and a table of all the solutions for the bottom equation, which would be a huge list, go on forever and ever. This is the only list. This is the only value that would be on both lists. Or now this is a complete sketch. When you could go to Desmos and graph it more accurately, or you could solve for y and graph it a little more accurately as well. But what it means is these lines intersect at the point 5, 0. The intersection is also the solution. It's just a visual way of representing it. Okay, so here is the new stuff. Example number 2. Oops. It's not working with me this morning. Well, we'll just roll. So, remember, our first step is to create opposites. And this one looks like it's going to be a little bit easier to create opposites. Like, for example, I know I can get opposite x's right now with doing just a little bit of easy multiplying. Because the opposite of negative 2x is positive 2x. So if I multiplied the top by 2, I would create a positive 2x on top. But then multiply that, or distribute that, to everything in the parentheses. So minus 4y equals 10. The bottom equation, I don't need or want to multiply it by anything because I already have a set of opposite x's. So when I add, the x's cancel out, and I created that to happen that way. However, this is the new special situation. When I add the y's, it also cancels out. It's 0. 0 y's. So there's nothing on the left side, which is the number 0. And on the right, when I add these numbers, I get 10. So now I wish my highlighter could work here. Oof. When you get rid of both variables, when they get canceled out, which is a special thing, it just, you try to cancel out one and it also cancels out the other one. It's unintentional, but when it does happen, it's either you have to analyze this equation right here, the 0 equal 10. That's false. So what that means is, to answer the question, what is the solution to this system, the answer is when you have a false statement, there is no solution. There is no coordinate pair that will show up on both lists of solutions, both tables for the equation. And if we were to graph this, this is just a sketch of the graph. This is not accurate, but it does most for an accurate graph. Oop. These lines are never going to intersect. They're parallel. They run along each side, along each other, the same distance apart forever and ever. So that solution, that intersection, does not exist at all. Let's try example 3. So example 3, I can create some opposite x's here pretty quickly and easily by multiplying the top by negative 2. Because the opposite of negative 4x is positive 4x. And negative 2 times negative 2 is a positive 4x. I'll continue distributing that through. So I've created opposite x's, so they've canceled. But again, whoa, the y's also cancel. So there's nothing on my left side. Now when I add the right side, I get 0. Now this is different. This is a true statement. 0 does equal 0. When it's a true statement, there are infinitely many solutions. In fact, we can't write them all down because our lines keep going forever and ever. So acknowledging the fact that it's impossible to write them all down, we say there are infinite solutions. And what does a graph look like for that? Well, that would be one of the lines, for example. The other line would be right on top of it. So as you can see, they're intersecting everywhere. There's an intersection, there's one, there's one, there's one. And it keeps going forever and ever. And everywhere it goes, that is an intersection because the lines are right on top of each other. So true statement makes the solution of, well, infinite solutions. Let's take a look at a little bit of your practice here first. Especially 1 through 4 are actually meant to be a little easier. However, a lot of people find them kind of tricky. And perhaps just using some logic, you can kind of see what's going to happen in number one. But our first step technically is to create opposites. So technically we want to multiply the bottom, or one of the equations, by -1. Multiplying by -1 turns that 3x into a -3x. But it also makes this -8y a positive 8y, and this 19 at the end a -19. But our main focus, at least for me, I'm looking at canceling out the x's because I see it looks like it's going to be easy to do. Although you could make the point that it's just as easy to cancel out the y's in this case. So I copied on the top equation, just brought that down right, or I brought that over right there, and I start adding, and sure enough, I think you probably realize, hey, my x's are going to cancel here along with my y's. So again, technically, and so this is a true statement, and so the solution is infinite solutions because it's a true statement. So you could, if you look at 2, 3, and 4, they're all fairly similar in terms of the left side is exactly the same, or the top left side is exactly the same as the bottom left side of the equations. So our trick here when that happens is to just multiply by -1, which is really the same as just taking the opposite of that equation. So if I were to multiply by -1 here, it would just make that a positive, that a negative, and that a negative, or the opposite. So if you want to save a little bit of step here on 1 through 4, a little bit of work writing, you can do that. So here we have cancelage, cancelage, and that gets you -1. So this is a false statement. There are no solutions. So your assignment on this worksheet is to do 1 through 10. And I can tell you right now, or if you look at the bottom, there are going to be 4 infinite solutions, 4 no solutions, and just like example 1, there are going to be 2 problems here that have 1 solution. So you'll have to calculate an x and a y, not necessarily in that order. One that's been challenging people here is number 8, because that first step of creating opposites isn't so easy here. So think about your least common multiples. What number does, if you actually focus on the y's, that'll get you a smaller least common multiple. It'll make your multiplier a little bit smaller. So list out your multiples of 9. List out your multiples of 12. And see what the smallest number is that they have in common. Then create that. And again here, since I've already done this problem, I know that it's going to be smaller with the y's. You could do this with the x's instead, and that would still get you the correct solution. It's your choice. And good luck with that. If you need more help, do the ones that I've done, study your notes, and if that doesn't help, come